kind of introduction. And yeah, my name is Shumon. I'm currently a postdoc at the UC San Diego. And yeah, as Jeremy introduced, I today present basically two topics on robotics and PD systems. The technology has been evolving so rapidly in the recent few years. Autonomous drones are growing to be capable of detecting objects using onboard sensors of LiDAR and camera, as well as the efficient motion planning to achieve some required tasks. Self-driving cars have been commercialized to revolutionize people's life as a novel transportation systems which do not require the presence of human drivers. 3D printing machines have been introduced in several industries to create a prototype of a new parts and enable mass production using CAD software. Electric vehicles start to appear in markets, which owns a high expectation for making future world much cleaner with sustainable and renewable energy. What do these scenarios have in common? In all the examples, component level technology is the sufficiently mature, such as high resolution camera and the accurate object classification algorithm. However, the composition into systems with intelligent functionality is still quite brittle, which renders a challenge when we close the loop from sensing to perception and action. For instance, autonomous cars still make mistakes, which could lead to a huge accident affecting people's lives. Also, in some cases, including 3D printing, performance requirements might not be met, which could cause a critical error in the product quality. The intelligent control system is needed to resolve these drawbacks. The task for control system is to design an input using a given output to achieve some objectives. For instance, in the case of self-driving cars, given an image sensor from the camera, the system detects the objects and changes the acceleration, deceleration, and steering accordingly to navigate the car to the destination without collision. There are essentially two questions in the control design arising here. What is the plant model and what are the tasks in the design? The plant model is often considered as a dynamical system, which is basically described by ordinary differential equation, ODE, or sometimes the partial differential equation, PDE. The tasks could be stabilization, safety, navigation, active sensing, etc. So in this talk, I essentially present two topics. The first one is the active sensing for ODE systems with applications to robotics. The second focus is the self-stabilizing control for ODE and Stefan PDE systems representing phase change dynamics. Let me present the active sensing problem first. The simultaneous localization and mapping, also known as CRAN, have been emerging as a method to construct a map of the unknown environment using the acquired data from the onboard sensors attached to the mobile robot. This demo shows the recent tool developed at MIT Sparks Lab, directed by Professor CRAN, for the novel SRAM method to estimate metric and semantic information by enabling mesh reconstruction and semantic labeling in 3D using visual inertial measurements. There are essentially two types of map representations. One is a randomark-based mapping to estimate the predefined randomark states, such as location or semantics, which gives a sparse map. The other is a volumetric mapping to estimate the occupancy or assigned distance at each voxel given by truncating the environment with mesh, which provides a dense map. Let's consider how to formulate the mapping program. We describe the robot motion as a continuous SE3 model, which has high fidelity in robot kinematics. And the observation model as a nonlinear function with respect to the robot pose state and the map state together with the Gaussian noise. We consider mapping by extended Kalman filter to obtain the mean and information matrix of the Gaussian brief given a history of the sensor states. The mean and information matrix are updated at every time. This enables one type of mapping by ETF. However, the question is how to plan and control the input U of the robot to improve the accuracy of the constructed map. This problem is known as an active mapping as one example of active sensing problem. For active mapping, we set our task as information theoretic objective to minimize the entropy of the map state given a history of the sensor state. Then, owing to the Gaussian property, the problem is shown to be equivalent to maximizing log determinant of the information matrix at terminal time. Hence, the mathematical problem we tackle is to maximize the log determinant of the information matrix with respect to the time sequence of the multi-step control input, subject to the robot motion model and the update of the information matrix. One special thing to note here is that the optimization problem does not necessitate the sensor states, and hence the computation can be done offline prior to obtaining the sensor input. There are prior work concerning the information theoretic active mapping. The earlier work considered a myopic planning and a continuous control space to optimize the cost only at the next time step, while many subsequent papers considered a non-myopic planning for enhancing the efficiency of the planned trajectory over a long time horizon, but the methods were limited to discrete control space. However, the trajectory of the robot evolves continuously over S33 space, and hence we set the goal of our work as developing a non-myopic planning for information theoretic active mapping over continuous control space. We developed a novel algorithm, named Iterative Covariance Regulation, ICR, to provide an optimal control sequence given an initial guess of the control sequence. What's happening inside ICR is an iteration of the forward path for the robot trajectory and backward path for the modification of the control input by the method of gradient descent. However, there are essentially two challenges in this problem. One is that the cost is non-differentiable due to a limited field of view of the depth sensor in practice, which renders the challenge in solving the optimization over the continuous control space. The other is that the cost is dependent on the time sequence of the multi-step control input, which has classically been solved by Pontryagin maximal principle and adjoint method, but the method was not generalized to matrix updates. To tackle the first challenge, we introduced the differentiable field of view via the following procedure. The idea is that we suppose that the map is fully measurable, but the sensor noise outside FoV field of view is infinite. Namely, the sensor matrix H is set to an identity matrix, and the sensor noise covariance matrix is set to a diagonal matrix whose diagonal element is to be formulated. Then we consider a relative vector Q of the coordinate Pj as just grid cell within the robot field of view coordinate. And using this relative vector Q, the diagonal element of the sensor noise covariance matrix is formulated as some finite magnitude related to the sensor noise magnitude if Q is inside F, and as infinite, approximately infinite if the Q is outside F. The next question is how to reformulate the set condition algebraically. We introduce a signed distance function, SDF, which returns the distance from the vector Q to the closest boundary of the set F with a positive sign if Q is inside F and with a negative sign otherwise. SDF has been utilized in computer vision tasks to represent the shape of the object. Then, using SDF and taking inverse, the inverse of the diagonal element V is given as a step function with respect to the SDF with the coefficient related to the sensor noise magnitude. Finally, to approximate the discontinuous step function by a continuously differentiable function, we introduce the probability function of the Gaussian CDF. And finally, the differentiable field of view is provided accordingly. This figure shows the visualization of the differentiable field of view, where the tuning parameter kappa represents the tunable parameter of the smoothness of the differentiable field of view. The second challenge is how to obtain the multi-step gradient of the cost. We derive the analytical gradient in the following steps. First, the gradient of the log determinant is given by a trace operator through calculus. And next, we incorporate the differentiable FoV matrices, and then apply a chain rule of derivative together with the differentiable FoV. And take derivative of Q by introducing a new state lambda as a perturbation of the S33 state with respect to the control input. Whose update rho is obtained by taking the gradient of the S33 motion model with respect to the U. This is how we derive the ICR as forward and backward iteration algorithm to obtain the optimal control sequence. We tested the performance of ICR in the simulated environment using real-world dataset of the occupancy grid map. Here we construct 2D mapping by a flying robot, which does not take into account the collision with the obstacles. We set the planning horizon as 5 seconds and the total time is 15 minutes. Here is the video of the result. The left movie shows the result of the occupancy mapping, and the right video shows the heat map of the acquired information. We can observe that the heat map is the acquired information. We can observe that the map is accurately constructed, and the exploration is done efficiently through homogeneous information acquisition. Through comparison to other benchmark methods, we can also observe the superior performance of ICR in terms of the information gathering. So to summarize, ICR is among the first methods to enable multi-step continuous control with a limited field of view. This is the main contribution of this work. So in ICR, we assume that the robot state is assumed to be deterministically known. But the next question is, what if the robot state is unknown and noisy? In such a scenario, we consider localizing the robot state from the sensor states by expanding the EKF to include the robot state dynamics as well. Then we consider control problem to reduce the gap between the optimized trajectory from ICR and the localized trajectory as a feedback control mechanism. So in this problem, we vectorize the SAC robot pose state and covariance matrix state and tackle a problem of obtaining the control policy as a feedback of the robot pose state and the covariance state from EKF. To solve such an stochastic optimal control, first we employ ICR to obtain the nominal trajectory under the noise-free dynamics. And next, we introduce the nominal vector and approximate the cost as a quadratic function by Taylor expansion, assuming the localization error is sufficiently small. Then we linearize the robot dynamics around the nominal trajectory and the cost as weighted sum of quadratic term for validating the linearization and approximated cost. Then the linear quadratic optimal control is analytically solved by extending extending the LQR to the inclusion of the bias term, since the cost includes the linear term by Bellman's optimality principle. This is how the active map SLAM problem is solved by combining ICR with LQR. The note that all the computation requires system matrices and hence the model-based design. And also, we replace the robot pose state by localized robot pose state obtained from EKF SLAM. Here is a diagram of the proposed ICR-LQR. First, the nominal trajectory is obtained by ICR, and then using this information, and the LQR gains are solved in an offline stage. Then, as an online execution, both feedback control associated with EKF SLAM is performed. Once some predefined time horizon is reached, the algorithm is returned to the initial condition and keeps repeating this process. We tested the active SLAM with a landmark-based mapping to estimate the position of the multiple landmarks in simulation. The left figure shows the robot trajectory with a pure ICR, and the right figure shows the trajectory with ICR-LQR. We can observe the superior performance of the proposed ICR-LQR in exploring the landmark uniformly with reducing the uncertainty of the landmark position. So there is one assumption we suppose so far about the field of view. When the field of view intersects with objects, anything behind it is not visible, even if the area is included in the original FoV. Such an occlusion of the FoV must be taken into account when we consider active sensing in an environment including obstacles. We tackle the problem by approximating the cost of the information measure. Here, the Shannon Mutual Information, SMI. In particular, we consider only the range sensor and logos mapping technique, which does not necessitate the sensor model as Gaussian. Instead, the SMI needs to be approximated to handle this scenario. We approximated it as a convex combination of the SMI in nearby viewpoints, while this the nearby view SMI is still not differentiable. We introduce a probit function to make a smooth approximation, similarly to ICR. Also, the SMI in the nearby viewpoints can be formulated in an occlusion-aware case, so the planning to optimize the resulting approximated cost is occlusion-aware. In addition to the approximated SMI, we also include the collision penalty and the sensor FoV overlap penalty to enhance the applicability of the method in practice. The resulting cost is both differentiable and occlusion and collision aware, and thus we apply the multi-step gradient descent technique in ICR. The proposed method is demonstrated in hardware robot experiment as shown in the video. The upper right corner shows the movement of the car robot, and the lower left corner shows the RGB image and depth from the camera sensor. And the constructed map is shown in the center. We can observe that the robot efficiently explore the hallway without getting too close to the walls to avoid the collision and occlusion, and the environment map is accurately acquired. So while the proposed method so far gives the offline planning of the motion of the given for a given environment, the obtained control cannot be directly applied to a new environment without recomputation. The next question is how to run a control policy from several available data of different environments, including indoor or outdoor or even the underground scenario. We consider an active landmark-based mapping to localize the multiple landmarks. The land control policy is trained with randomized number of the landmarks and the randomized initial condition of the robot state, landmark state and uncertainty. We develop a method to run a continuous control policy for the active perception. The control policy is set to a deep neural network, and the policy optimization is done by proximal policy optimization, PPO, which is a popular model-free RL algorithm over continuous control space. There are two special features in this algorithm. One is to introduce the differentiable FoV to stabilize the convergence of the training as a reward shaping. The other is to incorporate attention block in the network architecture to handle the varying number of multiple landmarks during the training. After sufficient amount of training, we tested the land control policy with 3 cases, 3, 5, and 8 number of landmarks, where the landmark position is randomized. We can observe that for all scenarios, the robot efficiently visits the landmarks. Also, the land policy is combined with volumetric mapping for a joint exploration and landmark localization task by setting the reward as the weighted sum of the 2 rewards. The performance is promising in terms of the exploration-exploitation policy to visit the landmark first and then explore the environment. The performance is also tested in a photorealistic simulation, which handles the real image sensor. Here, the RGB image is converted to the semantic information to tell which landmark it is, together with the depth information to know the relative distance from the robot within the square FoV. The demonstration shows the promising performance. Then next, I present the control for the safe stabilizing control task for the ODE and the Stefan PDE system in the second part. Can I proceed with this part, or is there any question at this moment? All right. Yeah, maybe I can proceed with the second part.
You can, Shumon. Sorry, you can.
All right, got it. Thank you. In the presence of obstacles and other robots, the planning in unknown environment needs to take into account for collision avoidance to ensure the safety of the operation. The penalty method mentioned earlier does not ensure the feasibility of the optimization problem. Thus, the question is whether we can synthesize the control for safety and other tasks, such as stabilization, from a systematic perspective with a probable performance. The recently control barrier function, CBF, and its quadratic programming-based control methods have been extremely emerging as a safe control design method by analogous formulation to the Lyapunov-based technique. Here we consider control program to stabilize the robot state at the origin with ensuring the safety subject to the robot dynamics given by a control-affine nonlinear ODE system. CBF is defined so that it returns non-negative value within the safe set, while CLF is defined as a positive function for any state X other than origin and becomes 0 at the origin. The classical CLF-CBF-QP formulation is given as minimizing the square norm of the control input and the slack variable subject to the constraints of CLF and CBF. While safety is ensured with this method, the stability is not guaranteed due to the slack variable here in CLF condition. Indeed, QP-based methods sometimes introduce the undesired equilibria on the boundary of the safe set. This simulation shows the result of the QP method from 3 initial conditions with an infinity-like shaped unsafe set. We can see that from all these initial conditions, the trajectory is stuck at the boundary of the safe set. We introduced a new idea to design safe stabilizing control by differential complementarity problem, DCP. The basics of DCP is as follows. DCP is given by a differential equation of y with additional variable z, which has a relation of the complementarity condition. Namely, the complementarity condition provides both z and here large C, capital C, maintained non-negative, while the cross product of the two of these two is kept at 0. Namely, especially in the case of z scalar, the z is set to be 0 if the condition C is positive, strictly positive, and z is activated to be positive value if the condition C reaches 0 value. The formulation represents such a mode switching, which have been applied in modeling dynamics with contacts as a hybrid system under constrained nonlinear optimization. Our new idea is to design a safe stabilizing control by DCP to switch the modes of the CLF and CBF constraints. In particular, the control input is decomposed into 2 parts with 2 variables of a scalar and vector for each WLUR and WH and UH bar. And the scalar value is utilized as a complementarity condition of the CLF and CBF. Here we can see that the safety is enforced more than the stability condition, since the CBF condition takes into account the sum of the 2 inputs, while the CLF condition only takes account the 1 input. Then, using a known result about the existence and the uniqueness of the solution to DCP, we can derive the condition and the appropriate choice for the vector parameters. This renders the CLF-CBF DCP control design. We tested the DCP control to the same simulated scenario in the previous slide. The figure illustrates that our the DCP control successfully achieves joint safety and stability, while the recent modified QP-based methods are still stuck at the boundary of the safe set. So this shows the superior performance of DCP-based methods in terms of the joint safe stabilization. While we only considered 1 robot to control so far, some more complicated tasks should be tackled by numerous robots. Then the question is how to handle such a swarm of robots. And modeling and control each robot 1 by 1 might struggle with the computational burden. And recently, modeling the swarm of the robots as a macroscopic perspective to give the PDE dynamics of the density of the robot have been proposed, which motivates us to expand the applicability of the control theory and methods to PD models. The motivation brought me the question, what is among the most challenging classes of the PD systems to be handled by control theory? There's one special PD model, the so-called Stefan problem, representing the dynamics of the phase change. The phase change appear a lot in the real world. The 3D printing is processed through melting the solid metal powder into the liquid metal and re-solidifying it layer by layer to fabricate the final desired shape of the texture of the final product. The charging and discharging in batteries renders the material's phase change of the particles in the electrodes to enable the energy storage. Melting of the Arctic sea ice is observed rapidly in the recent decade, and one research states that we will see ice-free summer in the Arctic by 2050. Sea ice melting could promote global warming through the loss of the solar energy reflection. The new thermal energy storage system with phase change has been developed for the utilization in spacecraft to neutralize the overheating through the combustion in the spacecraft. Let's consider a simple model of the Stefan PDE of that kind of thermal phase change. Let's consider a cylindrically shaped phase changing material, which is completely occupied by the liquid phase on the top region and the solid phase at the bottom region. For simplicity, we assume that the temperature and the liquid-solid interface is uniformly distributed along the cross-sectional area of the cylinder. There are two state variables. One is the temperature profile, which is distributed over space and changes in time. And the other one is the liquid-solid interface position, which changes in time due to the melting. We consider the heat input located at the surface of the liquid phase. The physics-based model of such a phase change is described by the Stefan problem, which is given by a PDE of the temperature distribution associated with the ODE of the liquid-solid interface. Due to the fact that the interface is defined as a domain of the PDE, and the dynamics is dependent on both the temperature PDE state and the interface position. Such a state-dependent moving boundary problem renders the total system as a geometric nonlinearity, which has not been treated by the control theory before my work. We consider the self-stabilization task to drive the liquid-solid interface position to the desired set point SR by manipulating the positive heat input QC, where the desired depth must be deeper than the final depth under zero input. Here, the safe condition about the liquid temperature to be greater than melting temperature needs to be satisfied. There are prior work which considers the control problem for similar systems. Some earlier work considered the control and estimator designs for linear parabolic PDE ODE system with constant domain, while the latter work considered the design for linear parabolic PDE with a time-varying domain. However, the Stefan problem, parabolic PDE with a state-dependent domain governed by ODE, resulting in nonlinear system, had not been treated by control theory before my work. I have tackled the control design problem by extending the infinite dimensional backstepping method to be applicable to the Stefan problem as follows. First, I define the reference error states to be stabilized at 0 states, and then develop a state transformation to convert the system to a newly defined state W, so that the system after the transformation has a stabilizing term in ODE. Finally, the control law is designed to cancel the redundant terms on the boundary condition, which appears through the transformation. And this is how we can design the backstepping based the control design for the Stefan PDE. And also the stability of the system is shown by applying the Lyapunov analysis. In particular, first we apply the Lyapunov analysis to the transform the WX system and using the equivalent stability property between the original and this W system through the transformation, we can guarantee the stability of the original problem. Then how to ensure the safety? We focus on the potential energy as a reference error states the about the temperature dynamics and the interface position, which satisfies a very simple, nice differential equation saying that the time derivative of energy is exactly same as the heat input Q, which is actually the energy balance and the first law of thermodynamics. Then the designed backstepping controller happens to be in the form of negatively proportional to the potential energy reference error. And then the form of the heat control input is equivalent to some sort of energy shaping control. And hence, with this nice property, we can guarantee the positivity of the heat control input, and which satisfies the input constraint in the problem. And then finally, by applying the maximum principle for parabolic PDE, which is the very well known analysis for the mass analysis of PDE, we can see that if the heat input Q is positive, then the temperature, the liquid temperature is greater than the melting temperature, which is physically very reasonable because it essentially says that if the heat input keeps injecting the positive heat input, then the liquid phase keeps melting without solidifying from the boundary of the heat input. Finally, we arrived at the theorem stating that here the control law is designed as a feedback of both temperature state and the interface position by extending the infinite dimensional backstepping method. And the theoretical statement states that the closed loop system satisfies the constraints of the state and input and the global exponential stability in H1 norm, which implies that the interface converges to the desired interface as time goes to infinity. As I said, the constraints are shown by maximum principle. Owing to the systematic property of the PDE backstepping method, I have further developed the design and theory to other situations, such as presence of the time delay and the model perturbation. And the digital sample data control setting, applying the well-known zero-order hold to the continuous time design, is shown to achieve the stability under the least assumption on the sampling time interval. In the presence of the actuator dynamics, self-stabilizing control has been developed by applying the high-order control barrier function and quadratic programming-based technique. And also, we have developed the event triggering mechanism for that. I have also demonstrated the performance of the control of the Stefan PDE in physical experiment of melting paraffin. As outputs, the surface temperature is measured by thermocouple, and the liquid-solid interface is measured by a ruler. The heat input is controlled by changing the input current, which is connected to the heater wire attached at the surface. Using this output, we employ estimator of the temperature as a copy of the plant and execute the design control input by the PD backstepping. For implementation, the profile is truncated at a finite number of grid points, and sampling is incorporated to enable the digital implementation of the proposed observer through time discretization, also by taking into account the future prediction of the output value from the sample data design. So this video shows the experimental result. The set point is set to 2 centimeter, which is depicted as a white line in image. And after controlling the heat input, the paraffin is melted from the top surface of this cylindrically shaped material, and the liquid-solid interface position is gradually converging to the set point position, 2 centimeter from the top surface position. And once the interface position arrives at the set point position, the melting process is almost stopped. So I have demonstrated the efficacy of the proposed control methods in applications to 3D printing in the simulated scenario. In polymer 3D printing, screw extrusion is considered, and the heat input needs to be adjusted based on the given operating mode for the fabrication speeds through feeding the polymer granules, where I show the desired stabilization for any given operating mode from slow to fast. In metal 3D printing, laser sintering process is considered, and generating a thin melt pool in micrometer scale, layer by layer, for fabricating the final object is successfully achieved. The estimation method I have developed was applied to climate model of the Arctic sea ice, where the temperature profile of the Arctic sea ice is accurately estimated only using measured value of the ice thickness and surface temperature. And I also focused on the charging and discharging process in the lithium-ion battery to estimate the state of the charge, which returns the remaining amount of energy inside the battery, which essentially shows on the right top of your laptop or smartphone. And we can see that our backstepping based estimator achieves the superior performance of this SOC estimation, even under the presence of noise, while we also compared the performance to the EKF-based estimation methods. And while the EKF-based methods does not show the sufficiently the fast convergence, even in the noise-free scenario. So this was the end. This is the end of my talk. So I essentially presented two topics of the active sensing and the safe stabilizing control for ODE and PDE systems. And yeah, thank you very much for your kind attention. And I'm very happy to take any questions.